Welcome. My name is Maximilian Katzmann, and in this video I want to talk about the joint work with Bläsius and Tobias Friedrich about how to efficiently approximate vertex cover on scale-free networks with an underlying hyperbolic geometry. In the vertex cover problem, we are given a graph and we want to find a smallest set of vertices such that each edge is incident to at least one vertex in the set. For example, this green vertex is incident to the green edges, and by adding it to the set, we would cover them. Together, all the green vertices cover all edges. Therefore, they form a valid vertex cover. Now, since vertex cover is an NP-complete problem, the best known algorithm to find a smallest cover has an exponential worst-case running time, and even if we were able to solve it in polynomial time, the graphs we encounter in the real world are sufficiently large such that even quadratic algorithms cannot process them in reasonable time. One way to avoid such large running times is to turn to approximation algorithms. There, the idea is to cut back on the qualitative performance of an algorithm, meaning we allow non-optimal outputs, to get an improved running time. A very simple greedy algorithm works as follows. We determine the vertex with the largest degree in the network, and then we add it to the cover and remove it from the graph together with its incident edges. Now we simply repeat this process. Find the vertex with the largest degree in the remaining graph, add it to the cover, and remove it from the graph. We do this until there are no more edges left in the graph. The vertices we collected on the way then form our vertex cover. This simple algorithm can be implemented easily in order to obtain vertex cover approximations even for large real-world networks. However, the question remains how well this algorithm performs with respect to the quality of the approximation. Well, it was shown that on general graphs, we cannot guarantee a better approximation ratio than log n using this approach. However, there is a simple two-approximation algorithm with linear running time, and the best-known polynomial approximation algorithm reduces this approximation ratio to 2 minus 1 over square root log n. Moreover, there is reason to believe that vertex cover is NP hard to approximate within a factor of 2 minus epsilon for a constant epsilon, and it is known that it is NP hard to approximate within a factor of square root 2. Now, despite all of these hardness results, it turns out that the simple greedy algorithm we have just seen actually performs very well in practice. In 2013, an empirical evaluation of this greedy algorithm showed that it obtains approximation ratios that are almost always very close to 1 on a selection of real-world networks. Here you can see our replication of their results together with an extension of the experiments on more networks. Now, all of these networks share some common properties. The first is heterogeneity, which means that the network contains a lot of vertices of low degree and only few vertices of high degree. So when we plot the degrees of the vertices on one axis and the fraction of vertices in the network that have this degree on the other axis, then we often find a distribution like this, which is called a power law degree distribution. The second property that is observed in many real-world networks is clustering, which refers to the following. When we take a vertex and look at its neighbors, then there are many edges among these neighbors, which means that together with the yellow vertex, they form a lot of triangles. So basically, high clustering means that there are many triangles in the graph. The previously mentioned experiments indicate that the greedy algorithm yields very good vertex cover approximations on networks that have these properties, which raises the question why this is the case. Now, unfortunately, we cannot analyze real-world networks theoretically. However, one way to explain such observations is to perform an average case analysis. In the context of networks, the process typically is as follows. We observe a phenomenon on graphs that we encounter in practice, we use network models to represent these real-world graphs, and we try to obtain an explanation of the phenomenon by analyzing the models. A model that has gained quite some popularity in recent years is the so-called hyperbolic random graph model. And following observations that optimal vertex cover solutions can be obtained efficiently from many real-world networks, it was shown that vertex cover can be solved exactly in polynomial time on hyperbolic random graphs. The proof relies on some interesting graph properties that also partially explain why the greedy approximation algorithm performs so well. Even more so, the model also predicts on which parts of the graph the greedy algorithm should be improved in order to get better approximation ratios. In our paper, we leverage this in order to create a new approximation algorithm, which is an adaptation of the greedy algorithm, that improves upon the performance of the standard greedy approach while maintaining a small running time. In particular, we proved the following main theorem, stating that an approximate vertex cover of a hyperbolic random graph can be computed in time proportional to the number of edges times the logarithm of the number of vertices, such that the approximation ratio is 1 plus little o of 1, asymptotically almost surely. Moreover, our experiments indicate that our adapted greedy algorithm also works well in practice. So this time we observed something in the model and were able to translate the results back to the real world. In the following, I will give a short introduction to hyperbolic random graphs, followed by a brief overview of the main ideas in the proof of the tractability of the vertex cover problem on hyperbolic random graphs, before using these insights to derive a new approximation algorithm, and eventually showing some experimental results that indicate that our insights translate back to the real world. The hyperbolic random graph model was introduced by Kryukov et al., and as the name suggests, hyperbolic random graphs live in the hyperbolic plane. The hyperbolic plane differs from the Euclidean plane in a very fundamental property, namely that in the hyperbolic plane space expands exponentially fast, while it only expands polynomially in the Euclidean plane. Therefore, when we try to project the hyperbolic plane onto Euclidean slides, the space gets distorted. Close to the center of the projection, which is the inner blue area, the space still looks somewhat Euclidean. But when we move away from the center towards the red areas, the representation is much denser, meaning in the red areas there's more hyperbolic space than appears to be. Now, since this sounds confusing, let me illustrate it on an example. This is a circle centered at the white point, which is at the center of our projection, and we have a line segment that divides the circle into two equal halves. Since the circle lies in the center of our projection and space expands equally fast in all directions, this circle just looks like a Euclidean circle. Now watch what happens when we move the structure into the red area. One half of the circle is still in the blue area, where the representation of space isn't as dense, but the other half covers an area that becomes more and more red. However, in the red regions there's more hyperbolic space than appears to be, meaning this shaded portion still makes up half of our circle. Now, in order to better understand how distances behave in the hyperbolic plane, let's consider two more points. One is just inside the circle and the other is outside of it. This is what a geodesic line looks like that represents the hyperbolic distance between the circle center and the inner point. Again, there is more space towards the red area than appears to be, which means that it's actually shorter to go through the center first. Now watch what happens when we move all points and the circle even further into the red area. The distances between these points have not changed, although they appear to be much closer now. One point is still just in the circle, and the line between the 2 points still goes through the center first. And the other point is still outside the circle. Thus, while the points appear to be closer, they actually aren't. So much for hyperbolic geometry. It remains to be determined how we can use it to generate a graph. We start by taking a disk in the hyperbolic plane, say the one that we started with, and then we sample points uniformly at random within this disk. Again, red space is represented much denser than blue space, meaning the points near the boundary of the disk only appear to be closer to each other than the ones in the center, when in fact they are not. So this actually is a uniform distribution. These points represent the vertices in our graph. Now we consider a circle of the same size as the disk around each vertex. Recall that we obtained the teardrop-shaped circle around our starting point by moving the starting disk towards the red area, which means that the two circles actually have the same size. And now we connect this point to all other points within this circle. When we do this for all points, we obtain our graph, which looks like this. Unfortunately, we cannot really see much of the graph that way, which is why we usually draw the edges between the vertices as straight lines for the sake of representation. Okay, so this is how we obtain our graph. Let's see why graphs generated that way are a good representation of real-world networks. First, consider our vertex near the boundary of the disk. The circle around it covers only a small portion of the disk and therefore contains only few other vertices. Consequently, this vertex has a small degree. In fact, the majority of the vertices near the boundary, and therefore the majority of the vertices in the graph, has a small degree. On the other hand, let's see what happens when we move this circle closer towards the center, say towards this vertex. The two circles still have the same size, but being closer to the center, this circle covers a larger portion of the disk. Consequently, this vertex has a much higher degree. This means that we have many vertices of low degree and only few vertices of high degree, and we obtain a power law degree distribution. Furthermore, if we consider two neighbors of this high degree vertex, then they have to be somewhat close to it, or else they wouldn't be its neighbors. Now, if they are both close to this vertex, then they cannot be too far away from each other. And this means that many of these neighbors also lie within each other's disks, and we obtain a lot of edges among these neighbors, so we have high clustering. Now we know the hyperbolic random graph model and why these graphs are a good representation of real-world networks. Let's take a brief look at why the vertex cover can be solved efficiently on such graphs. One main ingredient of the proof is the dominance reduction rule. It states that if there is a vertex U whose neighborhood contains a vertex V together with V's neighborhood, then there is an optimal vertex cover that contains U. Such a vertex U is called dominant, and the rule tells us that we can safely add all dominant vertices to the cover without impeding the search for an optimum. On hyperbolic random graphs, it was then shown that vertices that are not too close to the boundary of the disk dominate with high probability, meaning all these vertices can be safely added to the cover. Now recall that vertices that are closer to the center tend to have a higher degree. This means that the greedy algorithm that picks vertices in order of decreasing degree basically prefers dominant vertices and as a result chooses vertices that can be safely added to the cover anyway. However, once all high-degree vertices have been added to the cover and removed, most vertices have roughly the same small degree. From this point on, the greedy algorithm will basically pick the vertices at random. So in order to improve the approximation performance of the algorithm, one has to improve on the parts of the graph that contain the low-degree vertices. To this end, we propose the following adaptation of the greedy algorithm, which consists of two adjustments. First, we process the vertices in order of increasing radius, which is roughly equivalent to picking the vertices in order of decreasing degree in the original graph instead of always determining the highest degree vertex in the current graph after removing all previously selected vertices. Eventually, when enough vertices have been removed, the graph has been decomposed into small components, which we then aim to solve exactly. Now, of course, this happens gradually. As we remove vertices, more and more small components will be separated from the rest of the graph. To detect whenever this happens, we introduce our second adjustment. Whenever a vertex is removed, we perform breadth-first searches starting at each of the neighbors of the vertex. When such a search exceeds a given threshold, we stop and conclude that no small component was separated. When the search exhausts before reaching the threshold, we found a small component which we then solve exactly. As threshold size, we choose tau times log n for a constant tau. Finding an optimal vertex cover of such a component takes time exponential in the component size, which is still small due to our choice of the threshold. Moreover, since this is done at most once for every neighbor of every vertex, we can bound the total running time of the algorithm using the sum of the degrees of all vertices, which is in the order of the number of edges in the graph. Also note that the constant tau can be used to adjust the trade-off between the running time and the quality of the approximation. The larger tau, the larger are the components that we solve exactly. As a consequence, the running time increases. However, this also means that larger portions of the graph are solved exactly, which improves the approximation quality. No matter the choice of tau, the approximation ratio is always close to 1. To get an idea for why this is the case, let's take a look at how our algorithm performs on our hyperbolic random graph. We start with the vertex closest to the center, we add it to the vertex cover and identify its neighbors. Afterwards, we will remove it from the graph together with all its incident edges. Then we take a neighbor and perform a breadth-first search until the number of encountered vertices reaches our threshold. Then we take the next neighbor. And when doing this for all neighbors, we will find out that no small components were separated when removing this vertex. Next, we consider the vertex with the second smallest radius. Add it to the cover, find its neighbors, remove it and incident edges from the graph, and use breadth-first searches starting from the neighbors to find small components, which again doesn't happen here. However, eventually we reach a vertex where we find a small component. As before, we find its neighbors and remove it from the graph, and now while iterating the neighbors, this time there will be a breadth-first search where the number of encountered vertices does not reach the threshold. So we compute an exact vertex cover solution for it. And when doing this for the remainder of the graph, we end up with the following picture. Here, the separation between the green vertices that have been selected greedily and the yellow ones that have been part of small components that were solved exactly is pretty close to the separation between the vertices that were predicted to be safe and the rest of the graph. And this nicely shows while the standard greedy approach and our improved version behave basically the same initially, once the standard approach starts selecting vertices at random, we solve these parts exactly instead. Now by looking at this, we can already get an idea for why the performance of the algorithm is so good. The inner green part is optimal and the yellow part is optimal too. Basically, the only issue are the green vertices in the outer area. These are vertices that we don't know to be safe, but that are still added greedily to the vertex cover. Dealing with these is actually the most involved part of the proof in our main theorem, which works as follows. First, we make use of the fact that it has previously been shown that the size of a minimum vertex cover on hyperbolic random graphs is linear asymptotically almost surely. So to prove an approximation factor of 1 plus little o of 1, we only have to show that the number of vertices that we pick greedily but are not part of an optimal solution is sublinear in n. To this end, we find a threshold radius such that only sublinearly many vertices are contained inside and such that the removal of these vertices decomposes the graph into mostly small components. The last step is to show that the number of vertices in non-small components outside is sublinear in n, which also bounds the number of vertices that are added greedily there. To this end, we took a closer look at what happens near the boundary of a hyperbolic random graph. We discretized the disk into sectors in such a way that vertices cannot connect beyond empty sectors. Consequently, we can use empty sectors as delimiters between components. Then we showed that sectors are sufficiently likely to be empty such that most components span only few sectors, while there are only few components that span many sectors, which are indicated in red here. We then showed that there are only sublinearly many of these red sectors, and since the vertices are distributed uniformly at random, we could conclude that also the number of vertices in them is sublinear. Finally, we had to deal with the case where a component which spans only few sectors still contains a lot of vertices. But again, due to the uniform distribution of the vertices, it is unlikely that a lot of vertices are sampled into such a small region. For further details about the proof, we invite you to read our paper. Now, while this shows that our algorithm performs well on hyperbolic random graphs, it remains to be determined whether this also yields noticeable improvements on real-world networks. To this end, we performed experiments in order to compare our improved greedy approach with the standard one. Blue bars show the performance of the standard greedy approach, while green bars denote the performance of our improvement, where we set the parameter tau to 10, meaning we solved separated components of size at most 10 times log n exactly. On the x-axis, we see the networks that we considered, and the y-axis shows the obtained approximation ratios. First note that on the considered networks, using the improved algorithm never increases the approximation ratio compared to the standard approach, despite the potential differences in the considered vertex orders. Moreover, for 69% of the networks, using the improved algorithm reduces the excess percentage by more than 50%. This means that on these networks, the difference to an optimal solution has been more than halved. In conclusion, we have seen that the standard greedy approximation algorithm for the vertex cover problem performs well on real-world networks. The hyperbolic random graph model, which generates good representations of such networks, partially explains this phenomenon and indicates where the algorithm can be improved. Our analysis shows that the resulting adaptation has an approximation ratio of 1 plus little o of 1, while maintaining a quasi-linear running time. Finally, our experiments indicate that the obtained results also translate back to the real world. Again, we invite you to take a look at our paper for further details and to contact us if you have any questions.